January 1930. In a Cadillac showroom, the hood of a new automobile rose slowly above a chassis that already seemed unusually long. Beneath it sat an engine, unlike anything most customers had ever seen in a production car. Two banks of cylinders stretched along the frame, 8 on each side, forming a V16 whose complexity was visible before the engine even started. 16 pistons, 16 connecting rods, 16 combustion chambers, and the supporting machinery required to keep them working together occupied a space that made an ordinary 6-cylinder engine appear almost modest. Yet Cadillac had not created this machine for a racing circuit. It was intended for wealthy motorists who expected silence, smoothness, and effortless motion from some of the largest automobiles on American roads. The timing made the achievement even more striking. Only months earlier, Wall Street had collapsed and the United States was entering an economic crisis that would soon destroy businesses, fortunes, and millions of jobs. At precisely the moment when much of the country was being forced to reconsider what it could afford, Cadillac was offering an automobile whose engine seemed to represent the opposite philosophy. More cylinders, greater complexity, more craftsmanship, and a level of mechanical extravagance few buyers would ever experience. To understand why 16 cylinders could appear reasonable to engineers in 1930, it is necessary to return to an earlier period when the automobile itself was still learning how to behave like a refined machine. In the first decades of motoring, simply making a car move reliably was an achievement. Engines vibrated, controls demanded physical effort, roads punished mechanical components, and the difference between an inexpensive automobile and an expensive one could often be felt through the steering wheel, the floorboards, and the seat. Power delivery was not always smooth. A large piston firing inside a slow-turning engine produced a distinct mechanical pulse, followed by another and another as the crankshaft rotated. Engineers could increase engine size to move heavier cars, but larger cylinders could also bring greater reciprocating forces and more noticeable combustion impulses. For manufacturers attempting to sell luxury rather than basic transportation, this created a problem. Their customers were not merely paying to travel faster than a horse. They wanted the machinery to disappear beneath the experience. A prestigious automobile was expected to start easily, pull away without protest, climb hills without constant gear changing, and cruise with a degree of calm that suggested the engine was never working particularly hard. Adding cylinders offered one path toward that result. When the work of an engine was divided among more combustion chambers, power strokes occurred more frequently during each revolution. Individual pistons could be smaller for a given total displacement, and the engine's torque delivery could feel more continuous. The advantages depended on the layout, design, balance, and quality of construction, but the principle was attractive to luxury manufacturers. More cylinders could provide more than a larger horsepower figure. They could change the character of the car. This distinction would shape some of the most ambitious engines of the pre-war era. The first important escalation did not begin with 16 cylinders. It came with 12. Packard had already established itself as one of America's respected luxury manufacturers when engineer Jesse G. Vincent became closely associated with the company's technical direction. In the middle of the 1910s, Packard introduced the Twin Six, a name that described its architecture almost literally. 2 banks of 6 cylinders arranged in a V. A 12-cylinder automobile was not simply a larger version of a 6-cylinder car. It represented a different approach to refinement. Instead of relying on a small number of large combustion events, the V12 distributed its work across more cylinders. For a driver moving a heavy, touring body filled with passengers and luggage, the benefit was not something that required an engineering education to appreciate. The engine could deliver its force with an unusually smooth rhythm, pulling strongly without demanding that every increase in road speed be accompanied by obvious mechanical strain. That quality mattered in a period when luxury automobiles were expected to separate their occupants from the roughness of ordinary motoring. Packard did not invent the idea of the V12 in isolation, nor did the company create multi-cylinder engineering from nothing. Automobile development had always involved overlapping experiments, borrowed principles, competing designs, and lessons transferred from other forms of machinery. What Packard demonstrated was that 12 cylinders could be incorporated successfully into a prestigious production automobile and sold not merely as a technical curiosity, but as a defining feature of refinement. The Twin Six helped establish a language that luxury manufacturers would continue to speak for decades. Cylinder count became part of the car's identity. Buyers might never remove a cylinder head or understand firing intervals, yet the number itself carried meaning. 6 cylinders suggested sophistication. 8 could suggest greater power and smoothness. 12 implied that the manufacturer had gone beyond ordinary requirements in pursuit of something more exclusive. The mechanical architecture beneath the hood was becoming part of the social architecture surrounding the automobile. This did not mean that engineers were simply adding cylinders for appearance. Every additional cylinder brought cost. More pistons had to be machined, more connecting rods produced, more valves operated, more ignition components coordinated, and more surfaces lubricated. Manufacturing tolerances mattered. Cooling had to reach a larger and more complicated assembly. The crankshaft had to carry the forces generated by many cylinders without excessive vibration or failure. A multi-cylinder engine could offer impressive smoothness only if all those parts worked together with precision. Complexity, therefore, became both the price of refinement and evidence of it. In the luxury market, that trade could make sense. The price of the automobile already allowed manufacturers to use engineering solutions that would have been difficult to justify in inexpensive transportation. A wealthy buyer was not purchasing the simplest mechanism capable of moving from one city to another. The automobile was expected to convey status through its bodywork, materials, interior appointments, and increasingly through the sophistication hidden beneath the hood. The result was a subtle change in what engineers were being asked to achieve. Early automobiles had been judged by whether they could operate at all. Luxury cars were now being judged by how little of their mechanical effort reached the occupants. Smoothness became a form of performance. Silence became a technical accomplishment. The ability to accelerate a heavy car without forcing the driver to search constantly for the correct gear became evidence of abundant torque rather than laziness in design. 12 cylinders were particularly suited to this philosophy because their many firing events could make substantial displacement feel surprisingly gentle. Yet the V12 was only one answer. During the years that followed, another architecture began attracting manufacturers who wanted strong performance and exceptional smoothness without dividing the engine into two banks. 8 cylinders could be placed in a single line, creating an engine of striking length. The straight 8 imposed its own demands. Its crankshaft extended farther than those of shorter engines. Its block occupied considerable space, and the chassis required an engine compartment long enough to contain it. In a small, economical car, those disadvantages would have been difficult to ignore. In a prestige automobile of the 1920s, they could become almost theatrical. Long hoods were already associated with expensive machinery. The proportions created by a straight 8 reinforced that impression, turning the space ahead of the windshield into a visual declaration of mechanical authority. More important, the configuration could deliver the smoothness and power expected from a serious luxury or performance car. As automobile design entered the 1920s, the industry therefore had several ways to pursue the same broad ambition. Packard's 12-cylinder approach emphasized effortless refinement. Other manufacturers explored straight 8s, capable of combining smooth operation with increasingly ambitious performance. Racing experience, improved cylinder head design, better breathing, stronger materials, and more precise manufacturing were beginning to influence what engineers believed a large engine could accomplish. The question was no longer simply how many cylinders were required to make a car move smoothly. It was becoming a question of what kind of personality a manufacturer wanted its engine to possess. Some would seek quiet authority, others would pursue speed. A few would attempt to combine both qualities in machines whose engines were as technically impressive as the custom bodies surrounding them. By the end of the decade, the long straight 8 had become one of the most recognizable expressions of that ambition, and among the companies prepared to push the idea much further was a name that would come to represent the performance extreme of American luxury engineering, Duesenberg. Duesenberg entered that world with a philosophy shaped by competition. Fred and August Duesenberg had spent years building racing machines and engines, and the habits learned under those conditions did not disappear when the company turned towards some of the most expensive road cars in America. Racing punished weakness quickly. Poor breathing reduced power. Excessive weight mattered. Valve operation had to remain reliable at engine speeds that ordinary touring cars rarely approached. The lessons accumulated in workshops and on circuits gave the Duesenberg name a character different from manufacturers that emphasized quiet luxury above everything else. When the Model J appeared near the end of the 1920s, its straight 8 engine embodied that distinction. The displacement was large, roughly 420 cubic inches, or close to 6. 9 liters, but size alone did not explain why the engine attracted attention. Its cylinder head used dual overhead camshafts and 4 valves per cylinder, a level of sophistication strongly associated with high-performance engineering rather than conservative luxury car design. The result was an engine rated at approximately 265 horsepower in standard Model J form, a remarkable figure for an American production automobile of the period. What mattered even more was what that output allowed the car to do. The Model J was not a lightweight racing special. Depending on the coachwork fitted to its chassis, it could become an immense automobile with sweeping fenders, a long hood, a large passenger compartment, and the mass expected of a machine built for wealthy customers. Yet the engine gave it the ability to accelerate and travel at speeds that made many ordinary automobiles appear slow by comparison. Duesenberg had shown that the straight 8 did not have to be merely smooth. Properly designed, it could become the foundation of serious performance. The visual proportions reinforced the idea. A long row of 8 cylinders required a correspondingly extended engine compartment, and coach builders used that length to dramatic effect. The hood became part of the car's identity, stretching far ahead of the driver and suggesting that something substantial occupied the space beneath it. The relationship between appearance and engineering was not accidental. In this market, the customer was buying more than transportation. A large, sophisticated engine justified a long chassis, and the long chassis gave designers room to create bodies that communicated wealth before the engine was ever started. Yet beneath that theater was genuine technical difficulty. A straight 8 crankshaft was long. That length could create problems with torsional vibration and structural behavior if the engine were poorly designed. Lubrication, cooling, valve timing, and the rigidity of the block all mattered. The configuration offered naturally smooth characteristics, but smoothness on paper did not remove the need for careful engineering. Duesenberg's achievement lay in combining the basic virtues of the straight 8 with an unusually ambitious cylinder head and a performance objective that distinguished the Model J from many competitors. Other manufacturers also used straight 8s, but not everyone pursued the same level of output or mechanical complexity. For some companies, 8 cylinders were a path toward quietness and torque. For Duesenberg, they became part of a broader attempt to build an automobile capable of carrying luxury at a pace associated with performance machinery. That difference helps explain why raw cylinder count alone cannot describe the era. 8 cylinders could serve very different purposes depending on how the rest of the engine was conceived. The same would soon become true of 12 and 16. During the late 1920s, the American luxury market was crowded with competing interpretations of prestige. Packard had established a reputation for refinement. Cadillac had already built its identity around advanced multi-cylinder engines and precision manufacturing. Pierce Arrow, Lincoln, Peerless, Marmon, and others competed for buyers who expected exclusivity and engineering as well as bodywork. Manufacturers could differentiate themselves through styling, coachwork, comfort, durability, and reputation. But the engine remained one of the clearest mechanical symbols of rank. A buyer could see the length of the hood. Sales literature could announce the number of cylinders. A chauffeur could feel the torque when moving a heavy body away from the curb. The machine beneath the bonnet had become part of the language of wealth. This created an unusual form of escalation. A 6-cylinder engine could be highly refined, but it no longer sounded exceptional in a market where 8 cylinders were available. A straight 8 could be impressive, yet 12 cylinders carried a stronger suggestion of effortless operation. Packard had already demonstrated the appeal of the V12 years earlier. By the end of the 1920s, manufacturers understood that cylinder count could influence perception before a prospective customer ever experienced the car on the road. The number itself had become shorthand for complexity, exclusivity, and engineering expense. That did not mean every company automatically wanted more cylinders. Each additional component increased manufacturing difficulty and service requirements. A manufacturer had to balance prestige against cost, weight, packaging, and reliability. 12 cylinders already represented a substantial commitment. 16 went considerably further. The idea, nevertheless, became increasingly attractive to Cadillac. The company had both the industrial resources and the luxury market position to attempt something few competitors could match. Its engineers did not approach 16 cylinders simply as a way to produce the highest possible horsepower. That objective would have led toward a very different kind of engine. The V16 was conceived around qualities that Cadillac buyers valued: smoothness, quiet operation, strong torque, and the ability to move large custom-bodied automobiles with minimal sensation of effort. Dividing the work among 16 cylinders created frequent combustion events and allowed the engine to deliver power with remarkable continuity. The complexity that would have made such an arrangement difficult to justify in an inexpensive automobile became part of its appeal at the top of the market. There was another advantage. 16 cylinders offered Cadillac a mechanical statement that could not easily be confused with ordinary luxury. A V8 could be powerful. A V12 could be prestigious. A V16 stood apart simply because so few manufacturers were prepared to accept the cost and difficulty of producing one. Development, therefore, took place in an atmosphere where engineering and marketing were inseparable. The engine had to function with the refinement expected of Cadillac, but its very existence also communicated that the company possessed the technical and manufacturing capability to create something beyond normal requirements. The timing, though, could hardly have been more dangerous. Throughout much of the 1920s, expensive automobiles had flourished in an economy that seemed capable of supporting ever greater displays of wealth. Custom coach builders created bodies tailored to individual customers. Luxury manufacturers invested in engines and chassis that assumed a continuing market for extravagance. Then, the financial structure beneath that confidence began to fracture. The stock market crash of October 1929 did not instantly transform every aspect of American life, but it marked the beginning of a collapse that would deepen dramatically. Businesses failed, credit contracted, industrial production fell, unemployment rose, the number of people willing and able to purchase the most expensive automobiles could only shrink as the crisis intensified. Cadillac's V16 was already too far advanced to belong to a world redesigned around austerity. When it reached the public in January 1930, it arrived as a product conceived during one economic era and sold into another. The contradiction was visible in the machine itself. 16 cylinders represented precision, labor, material, and expense at a moment when millions of Americans were about to discover how scarce all of those things could become. Yet, from an engineering perspective, the car did what Cadillac intended. The V16 was not a crude attempt to win a numerical contest. Its power delivery emphasized calm authority. Heavy bodies could move without the harshness that might accompany a smaller engine working closer to its limits. The mechanical complexity remained largely hidden from the occupants, which was precisely the point. A luxury engine reached its highest expression when the passenger experienced the result without being forced to notice the effort required to produce it. Cadillac had therefore pushed the logic of multi-cylinder refinement to an extraordinary level. 16 cylinders were no longer an experimental curiosity. They were available in a production luxury automobile, supported by one of America's largest and most capable manufacturers. For a brief moment, the escalation appeared to have reached its natural summit. But Cadillac was not the only company that had been thinking about 16 cylinders. Howard Marmon and the engineers around him were pursuing their own interpretation of the same idea, and unlike Cadillac, they intended to combine the unusual smoothness of a V16 with an aggressive effort to control the weight that such complexity normally imposed. Howard Marmon approached the 16-cylinder problem from a different direction. His company had never possessed the industrial scale of General Motors, and that limitation made unnecessary weight and complexity especially dangerous. If Marmon was going to build an engine with 16 cylinders, the design could not simply become a heavier imitation of Cadillac's achievement. The solution took shape around an unusually ambitious use of aluminum. The Marmon 16 employed a 491 cubic inch V16, roughly 8 liters in displacement, with an aluminum alloy block and steel cylinder liners. Producing about 200 horsepower, it delivered the kind of smooth, abundant torque expected from an automobile intended to compete at the highest level of the American luxury market. The figures were impressive, but the engineering philosophy behind them mattered more. Aluminum offered a way to reduce mass in an engine that otherwise threatened to become enormous simply because of the number of components it contained. A V16 required 16 pistons moving through 16 cylinders, a crankshaft capable of carrying their combined forces, valve gear for each combustion chamber, extensive lubrication passages, cooling capacity, ignition equipment, and a structure rigid enough to hold the entire assembly in alignment. Marmon's engineers were therefore attempting something more subtle than adding cylinders. They were trying to preserve the advantages of 16 while resisting some of the penalties that 16 naturally imposed. That effort gave the Marmon engine a character distinct from Cadillac's, even though the two cars would inevitably be compared. The Cadillac V16 had already demonstrated what a large corporation could accomplish when refinement, manufacturing precision, and prestige were combined in a flagship automobile. Marmon's response carried a different kind of risk. The company was smaller, its resources more limited, and the expense of creating such a sophisticated engine had to be recovered from a market that was deteriorating almost as quickly as the car could be developed. By the time the Marmon 16 reached customers, the Depression was no longer an ominous possibility visible beyond the showroom windows. It had become the dominant economic reality of American life. Industrial production had fallen sharply. Banks were failing. Unemployment was spreading through communities that only a few years earlier had participated in the confidence of the 1920s. The number of customers capable of ordering an automobile at the extreme upper end of the market had contracted, and even people who retained substantial wealth had reasons to become more cautious about displaying it. Against that background, the Marmon 16 appeared almost paradoxical. Its engineering represented years of effort directed toward creating a quieter, lighter, more powerful luxury engine at precisely the moment when the economic foundations supporting such an automobile were collapsing. The contradiction did not make the machine less accomplished. It made its commercial prospects far more difficult. A 16-cylinder car was expensive long before the body was fitted. The engine alone demanded numerous precision machine parts, and every additional component introduced another opportunity for cost during manufacturing, assembly, adjustment, and later service. The chassis had to accommodate the size and torque of the power plant. Cooling systems had to be sufficient for a large engine operating inside a long, tightly enclosed hood. The driveline, brakes, suspension, and tires all belonged to an automobile whose mass and performance exceeded those of ordinary transportation. Once a customer selected elaborate coachwork, fine upholstery, bright work, instruments, and the countless details expected in a luxury car, the final price entered a world occupied by a tiny fraction of buyers. During prosperous years, scarcity itself could strengthen the appeal of such machinery. During a severe economic contraction, scarcity of buyers became a threat to survival. Cadillac could absorb that reality within the resources of General Motors. Marmon had far less room for error. This difference shaped the historical meaning of the two V16s more than a simple comparison of horsepower ever could. The Cadillac was evidence that a major manufacturer could push refinement to an extreme and sustain limited production of a highly complex flagship. The Marmon 16 showed what could happen when a smaller company committed itself to comparable ambition at the worst possible moment. Howard Marmon's engineers had created a technically sophisticated automobile, but engineering excellence could not manufacture customers who no longer existed. Nor could technical merit protect a company from the broader collapse of the luxury car market. The Depression exposed a truth that had been easier to ignore during the previous decade. The ultimate automobile was not defined only by what could be engineered. It was also constrained by what could be produced, sold, maintained, and justified economically. That pressure began changing the meaning of extravagance. In the 1920s, additional cylinders could be presented as evidence that a manufacturer had gone beyond ordinary standards. By the early 1930s, the same complexity invited uncomfortable questions about cost. Was the extra smoothness of 16 cylinders worth the additional manufacturing effort? Could 12 provide nearly the same sense of effortless movement with fewer components? Could an 8-cylinder engine become more powerful through better breathing and combustion rather than by doubling its cylinder count? Manufacturers did not answer those questions in the same way. Packard, whose earlier Twin Six had helped establish the prestige of 12-cylinder motoring, returned to the V12 concept rather than following Cadillac and Marmon to 16. That choice reflected the fact that the industry's development was never a simple staircase leading inevitably toward more cylinders. 12 could already provide extraordinary smoothness and strong torque for heavy luxury cars. For Packard, the configuration remained capable of supporting the company's reputation without requiring the mechanical escalation represented by a V16. The difference became increasingly meaningful as the Depression continued. Cadillac, Marmon, Packard, and Duesenberg were all building automobiles for wealthy customers, yet their engines embodied different answers to the same set of expectations. Duesenberg sought performance through an advanced straight 8. Packard continued to value the refined authority of 12 cylinders. Cadillac used 16 to create a level of smoothness and prestige that few competitors could match. Marmon combined 16 cylinders with an effort to control weight through advanced materials. None of these solutions can be understood properly by reducing them to a chart of displacement and horsepower. They reflected different assumptions about what the finest automobile should feel like and how much complexity a manufacturer was willing to accept in order to create that sensation. The marketplace, however, was beginning to judge those assumptions with increasing severity. Duesenberg's spectacular automobiles remained beyond the reach of almost everyone. Marmon's financial position weakened despite the technical quality of its 16. Even the strongest luxury manufacturers had to consider whether elaborate multi-cylinder engines could continue to justify themselves in sufficient numbers. The Depression did not instantly eliminate large engines, nor did it end the desire for prestige. Wealthy buyers still existed, and manufacturers continued refining their most expensive products. Yet the direction of engineering was becoming less predictable. The central question was shifting. During the great cylinder escalation, one obvious route to greater smoothness and effortless torque had been to enlarge the engine, divide its displacement among more cylinders, and accept the accompanying complexity. Another route was now becoming increasingly important, especially in competition: improve the amount of useful power obtained from a smaller package. Racing engineers had strong reasons to pursue that alternative. Weight could determine whether a car changed direction quickly. Engine size influenced the chassis surrounding it. Fuel consumption affected race strategy. Regulations could limit displacement. A large engine remained useful, but merely increasing its dimensions could no longer solve every performance problem. Engineers therefore pushed harder on breathing, compression, valve operation, rotational speed, and methods of forcing more air into cylinders. Supercharging offered one particularly powerful answer. Instead of creating additional capacity only by enlarging the engine, a supercharger could supply the cylinders with a denser charge of air, allowing more fuel to be burned and substantially increasing output from a given displacement. The principle did not make large engines obsolete, and it carried its own mechanical demands, but it altered the relationship between physical size and power. An engine no longer needed 8 liters and 16 cylinders to produce a figure that would have seemed extraordinary only a few years earlier. On American boulevards, the long hoods of Cadillac, Marmon, Packard, and Duesenberg still represented the summit of a particular vision of motoring. On European racing circuits, another vision was gathering speed, one in which engineers increasingly asked not how much engine they could place beneath the hood, but how much performance they could extract from every liter already there. The change in emphasis became increasingly visible as racing engineers experimented with ways to increase output without allowing engines to grow without limit. Displacement still mattered. and large engines remained common in many forms of competition. But a new set of priorities was becoming impossible to ignore. Engineers were learning that the amount of power produced by an engine depended not only on how much air and fuel its cylinders could contain, but on how efficiently those cylinders could be filled, emptied, cooled, lubricated, and made to operate at higher speeds. Better cylinder head design allowed gases to move more freely. Improved valve arrangements helped engines breathe at rotational speeds that would have challenged earlier machinery. Stronger metals permitted components to survive greater loads. Fuels improved, ignition systems became more dependable, and supercharging offered a direct way to increase the mass of air entering an engine without simply enlarging every cylinder. The result was not the immediate disappearance of the large, naturally aspirated motor. Instead, engineers now possessed additional tools, and those tools weakened the assumption that greater physical size was always the most direct path to greater performance. European Grand Prix racing made the shift especially clear. Competition imposed priorities that were very different from those surrounding a Cadillac V16 or Packard 12. A luxury automobile could carry considerable mass if that weight purchased silence, durability, prestige, and relaxed torque. A racing car had to accelerate, brake, and change direction while remaining reliable under prolonged mechanical stress. Every kilogram influenced the rest of the machine. A larger engine required more structure around it, affected weight distribution, and could increase fuel consumption. Racing regulations could also limit displacement, forcing designers to extract more performance from a fixed capacity rather than simply making the engine larger. These pressures encouraged solutions that would have seemed unnecessary in a chauffeur-driven limousine. Supercharging became one of the most important. A naturally aspirated engine depends on atmospheric pressure and piston movement to draw air into its cylinders. A supercharger compresses the intake charge before combustion, allowing a greater mass of air to enter the same space. More oxygen makes it possible to burn more fuel, and the resulting increase in combustion energy can raise power dramatically. The concept brought its own penalties. Compressing air generates heat. The supercharger itself consumes power. Internal components face greater loads, and poor control of combustion can damage an engine quickly. Yet when the system is designed properly, the effect on performance can be profound. By the later 1930s, racing engines were demonstrating power outputs that would have required far greater displacement under earlier assumptions. Mercedes-Benz's Grand Prix machinery provided a striking example. The W154 used a supercharged V12 of roughly 3 liters, far smaller in displacement than the 8-liter Marmon 16. Yet, in its most highly developed form, it could produce well over twice the Marmon's approximate 200 horsepower. The comparison needs care because the two engines were created for entirely different tasks. Marmon's V16 had to propel a heavy, luxury automobile smoothly through ordinary road use, start reliably, tolerate varied conditions, and deliver its performance without demanding the constant attention expected from a racing machine. The Mercedes engine existed to compete at extreme speeds and could accept compromises that would have been unreasonable in a production luxury car. Even so, the contrast reveals how rapidly the relationship between displacement and power was changing. An engine no longer had to be physically enormous to produce an enormous number. This did not make the American multi-cylinder luxury cars suddenly obsolete. Their customers were buying qualities that racing technology could not automatically provide. A highly stressed competition engine that produced tremendous output from a small displacement might be noisy, demanding, expensive to maintain, and unsuitable for the relaxed operation expected from a prestige automobile. Cadillac's 16 cylinders offered something different: power delivered with remarkable continuity and little sense of strain. Packard's 12-cylinder cars pursued a similar kind of authority through a less extreme layout. Duesenberg occupied unusual territory by combining luxury with a straight 8, whose engineering reflected performance thinking. The important development was that the industry could now see multiple routes toward excellence. Cylinder count had lost its position as the only obvious measure of mechanical ambition. That realization became more significant as economic pressure continued throughout the 1930s. The Depression did not affect every luxury manufacturer in the same way, but it narrowed the market in which extremely expensive machinery could survive. Marmon's position deteriorated until automobile production ended, leaving the 16 as one of the clearest examples of advanced engineering arriving at a moment when engineering alone could not determine commercial success. Duesenberg also remained tied to an exceptionally small group of wealthy customers, and the company's road car production eventually disappeared. Packard survived, but its decisions increasingly had to account for a market broader than the narrow world of custom-bodied prestige cars. Cadillac had the protection of General Motors and could continue to develop luxury automobiles from a stronger corporate foundation. Yet even Cadillac could not ignore changes in cost, demand, and manufacturing efficiency. The enormous engines of the previous decade were becoming more difficult to justify as symbols of progress simply because they contained more cylinders. Packard's continued use of 12 cylinders illustrates why the industry's evolution cannot be reduced to a race in which 16 automatically defeated 12. A well-designed V12 already possessed many of the characteristics luxury buyers wanted. Its firing frequency could provide exceptional smoothness, its torque suited heavy automobiles, and its arrangement was more compact in length than a comparable straight engine. Moving from 12 cylinders to 16 brought additional refinement and exclusivity, but the practical benefit did not necessarily rise in proportion to the number of extra parts. For a manufacturer evaluating cost, serviceability, production volume, and market demand, the question became increasingly difficult. How much additional complexity would a customer actually pay for? The same reassessment affected the straight 8. Its long form had once complemented the proportions of prestige automobiles beautifully, but packaging efficiency was becoming more important. A long engine required a long chassis and influenced the position of the passenger compartment. As manufacturers began thinking more carefully about interior space, production efficiency, and overall vehicle proportions, the physical elegance of a straight 8 could become an inconvenience. None of these changes happened overnight. Large engines, straight 8s, and 12-cylinder cars continued to be built, and prestige buyers still valued mechanical abundance. The historical shift was more gradual. The qualities once obtained primarily through size and cylinder count were increasingly available through improvements elsewhere in the machine. Better engine mounts could isolate vibration. More precise manufacturing reduced roughness. Advances in combustion allowed greater efficiency. Transmission development made it easier to keep an engine operating in a useful speed range. Stronger materials supported higher rotational speeds and higher compression. Engineers were learning that refinement could be created by coordinating many systems rather than concentrating every solution inside an ever more elaborate engine block. By the end of the decade, automobile engineering stood between two worlds. One remained visible in the long hoods and imposing radiators of Packards, Cadillacs, Duesenbergs, and other prestige cars whose proportions had been shaped by large multi-cylinder engines. The other was emerging through racing laboratories, improved production methods, and a growing understanding that useful power depended on efficiency as much as capacity. The transition might have continued gradually if industrial development had been allowed to follow its existing course. History imposed a far more abrupt interruption. In September 1939, Germany invaded Poland, and Europe entered a war that would redirect engineering talent, manufacturing capacity, strategic materials, and national priorities on a scale the automobile industry had never experienced. Factories that had competed to produce elegant road cars increasingly turned toward military requirements. Engineers worked on aircraft engines, trucks, armored vehicles, communications equipment, and the countless mechanical systems demanded by modern warfare. Aluminum, steel, rubber, fuel, and machine tools acquired strategic significance. Civilian luxury became secondary to production measured in military necessity. The effect spread beyond Europe. Once the United States entered the war, American automobile manufacturers converted enormous portions of their industrial capacity to military production. Assembly lines that had once produced passenger cars were redirected toward engines, trucks, aircraft components, weapons, and other equipment. Civilian automobile production was curtailed as the industry's resources were absorbed into the war effort. For the great multi-cylinder luxury engines, this interruption did more than pause production. It severed the connection to the economic and social world that had created them. The pre-war customer who ordered a custom body on an immense chassis belonged to an era of highly individualized luxury manufacturing. Coach builders, prestige marques, long engine compartments, formal chauffeur-driven bodies, and extraordinarily complex power plants had evolved together within a particular market. When civilian automobile production eventually returned, manufacturers would confront different buyers, different production expectations, and a society transformed by years of war. Drivers would still want quietness. They would still want torque, acceleration, comfort, and status. The engineering goals had survived. What no longer seemed inevitable was the belief that achieving them required 12 cylinders, 16 cylinders, or 8 cylinders arranged beneath a hood that seemed to stretch toward the horizon. When civilian automobile production returned after the war, the basic desires of luxury buyers had not disappeared, but the industrial logic surrounding those desires had changed. Drivers still wanted quiet engines, strong acceleration, low vibration, dependable starting, and the ability to move heavy cars without constant gear changes. What had changed was the range of engineering methods available to achieve those qualities. Improvements that had been developing before the war now advanced within a manufacturing environment shaped by enormous wartime experience in metallurgy, precision machining, lubrication, fuels, cooling, and mass production. Engineers no longer had to solve every problem of refinement by dividing an engine's work among more and more cylinders. Better combustion chambers could extract more useful energy from fuel. Higher compression ratios improved efficiency and output. More precise machining allowed components to operate with tighter tolerances. Stronger materials helped engines survive greater rotational speeds. Ignition systems became more dependable, lubrication improved, and transmission design gave drivers access to power without requiring the extraordinary low-speed flexibility once associated so strongly with very large multi-cylinder engines. The objective remained familiar. The path toward it was becoming shorter, lighter, and less expensive. In the United States, the V8 emerged as one of the most successful expressions of that new balance. The layout was not new, and Cadillac itself had built V8 automobiles long before the war, but post-war development gave the configuration increasing importance. A V8 could provide substantial displacement and torque without the extreme length of a straight 8. It required fewer repeating components than a V12 or V16, reducing the number of pistons, connecting rods, valves, ignition elements, and machining operations needed to produce a powerful engine. For manufacturers attempting to build automobiles in larger numbers while controlling cost, those advantages mattered enormously. A well-developed V8 could move a heavy car with authority, fit within a more compact engine bay, and deliver the kind of performance that earlier buyers might have associated with far more elaborate machinery. None of this made 16 cylinders technically meaningless. It changed the economic question. During the height of the pre-war luxury market, engineers and wealthy customers could justify extraordinary complexity because exclusivity itself had value. In the post-war industry, a manufacturer increasingly had to ask whether a refinement gained through 4 or 8 additional cylinders was worth the extra cost of designing, producing, servicing, and packaging them. For most passenger cars, the answer became difficult to defend. The straight 8 faced a different problem. Its smoothness and prestige had made it an attractive choice during an era of long hoods and formal body proportions, but the configuration occupied considerable length. As automobile design evolved, manufacturers wanted greater freedom to move the passenger compartment forward, shorten the space devoted to the engine, improve interior room, and package vehicles more efficiently. A long crankshaft and extended block worked against those priorities. The straight 8 had not suddenly become a bad engine. The car around it had changed. This distinction is essential to understanding why so many pre-war layouts disappeared. Technologies rarely vanish because engineers collectively discover that their predecessors were foolish. They disappear when the balance of advantages and disadvantages shifts. The straight 8 had solved real problems when smoothness, large displacement, and long luxury car proportions worked together. Once shorter engines could produce comparable power and refinement, its physical length became harder to justify. The V12 survived longer because its two-bank arrangement allowed 12 cylinders to fit within a relatively compact length, and the layout continued to offer the smoothness and prestige that appealed to manufacturers at the extreme end of the market. In later decades, 12 cylinders would appear in some of the world's most celebrated luxury and performance automobiles. That survival reveals something important about the pre-war cylinder race. The underlying idea was never entirely abandoned. Instead, it became specialized. 12 cylinders no longer represented an obvious destination for mainstream prestige engineering, but in applications where cost mattered less and exceptional smoothness or exclusivity remained valuable, the concept retained a purpose. 16-cylinder road engines became far rarer because the additional complexity offered diminishing practical returns once other technologies improved. The question was no longer whether engineers could build a V16. Cadillac and Marmon had already proved that they could. The question was whether a customer would receive enough additional value from 16 cylinders to justify everything required to manufacture and maintain them. For most of the market, a smaller engine answered the same needs more efficiently. Looking back across the pre-war period, the 4 major machines at the center of this story no longer appear as competing entries in a simple contest of size. Each represented a distinct answer to the expectations of its time. The Duesenberg Model J showed how a large, straight 8 could combine substantial displacement with sophisticated valve operation and serious performance. Its significance lay not in the fact that it possessed 8 cylinders, but in what engineers made those cylinders capable of doing. Packard demonstrated a different kind of achievement. Its 12-cylinder automobiles emphasized smooth authority, proving that abundant power could be delivered without the engine drawing attention to its own effort. Cadillac pushed the idea of mechanical refinement to an extreme with the V16, turning cylinder count into a visible expression of engineering prestige. Marmon approached the same number with a stronger concern for weight, using aluminum extensively in an attempt to prevent 16 cylinders from becoming an unnecessarily massive burden. The fact that the Marmon 16 arrived during a collapsing luxury market does not diminish the thought behind it. Instead, it reveals the vulnerability of engineering when historical circumstances move faster than product development. A machine can be technically successful and commercially doomed at the same time. That lesson may be the most important reason the giant engine era deserves more than nostalgic admiration. The cars were not merely extravagant artifacts created by manufacturers obsessed with size. They were attempts to solve specific problems within the limits of contemporary technology. Vibration mattered because engine mounts and structural isolation were less advanced. Low-speed torque mattered because transmissions offered fewer ratios, and drivers expected large cars to move smoothly without constant shifting. Combustion control was far less precise than it would become decades later. Manufacturing tolerances, fuels, lubrication, and materials imposed constraints that modern designers would approach very differently. Adding cylinders could make power delivery smoother at a time when other solutions were limited. Large displacement could provide relaxed torque without requiring an engine to operate near its mechanical limits. Long hoods were acceptable because the automobiles themselves were designed around different proportions and different expectations of space. Once those conditions changed, the engineering answer changed with them. The disappearance of the great pre-war engines, therefore, did not mean that their creators had pursued the wrong objectives. Modern automobile designers still pursue almost all of the qualities that Packard, Duesenberg, Cadillac, and Marmon were trying to achieve. They still want engines and powertrains that deliver acceleration without harshness. They still work to reduce vibration, noise, mechanical losses, and unnecessary weight. They still search for ways to make power available immediately when the driver demands it. What has changed is the machinery used to achieve those results. Electronic fuel injection can meter fuel with a precision early carburetors could never approach. Computer-controlled ignition can adjust combustion continuously. Variable valve systems allow an engine to behave differently at low and high speeds. Turbochargers can force additional air into a comparatively small displacement. Modern transmissions keep engines operating within efficient ranges. Hybrid motors can provide immediate torque without adding cylinders at all. Materials and manufacturing methods allow components to survive loads that would have demanded very different dimensions in the 1930s. The ultimate achievement of later engineering was therefore not the rejection of the goals pursued by the giant engines, but the ability to reach those goals with less mechanical excess. That reality makes the Cadillac showroom of January 1930 look different when we return to it. Beneath the long hood, 16 cylinders no longer seem like an irrational stunt. They belong to a specific moment when the finest automobile was expected to conceal its effort behind abundant machinery. The owner of such a car was not supposed to feel 16 individual pistons working. The success of the design lay precisely in making all of that complexity disappear into smooth motion. That same desire had helped Packard establish the appeal of 12 cylinders years earlier. Duesenberg demonstrated that sophisticated high performance could coexist with luxury. Marmon showed how far engineers were willing to go to reduce the penalties of an extreme configuration. Then economics, new technology, changing vehicle proportions, and war altered the environment in which those ideas had made sense. The giant engines faded because the world around them moved on, not because power, refinement, or prestige ceased to matter. Those qualities remained, and the automobile industry continued pursuing them with increasingly sophisticated tools. There was a time when the finest motor car might carry 8 cylinders in a single line, 12 arranged in 2 banks, or 16 working with such regularity that their combined effort seemed almost invisible. These engines were expensive, complicated, and often physically immense, but they were not products of engineering ignorance. They were answers to the ambitions and limitations of their era. Eventually, greater power became possible from smaller displacement. Smoothness became less expensive to create, and complexity no longer needed to announce itself through cylinder count. Yet for a brief period before the Second World War, automobile manufacturers were willing to ask a very different question from the one that guides much of modern engineering. They were not asking how little machinery could accomplish the task. They were asking how magnificent the machine could become.